Hello everyone, welcome to my presentation on applications of calculus. My name is Fernando Hartono, and today I'll walk you through how calculus, an essential mathematical tool, finds applications in economics, solid geometry, and physics. The topics we'll cover include derivatives in economics, the Washer method for finding volumes, and moments at the center of mass. Let's dive in. This slide gives a roadmap of our journey today. First, we'll explore the application of derivatives in economics to understand concepts like cost, revenue, and profit functions. Next, we'll look at the Washer method, a powerful tool for calculating volumes of solids of revolution. Finally, we'll discuss moments at the center of mass, which are critical in understanding how forces and mass distributions works in real-life contexts. Let's start with derivatives in economics. Let's start with understanding the cost function, a fundamental concept in economics. The cost function, typically represented as C of X, describes the total cost incurred by a company in producing X units of a product. This function accounts for two key components: fixed costs, costs that remain constant regardless of the production level; variable costs, costs that depend on the quantity of production. The derivative of the cost function, denoted as C prime of X, is known as the marginal cost. This measures the additional cost incurred to produce one extra unit of a product. In mathematical terms, C prime of X actually means the rate of change of C of X. Here is an example. If a company's cost function, C of X, equals to 2x squared plus 10x plus 100, notice that 100 is the fixed cost and 2x squared plus 10x is the variable cost as they depend on x. Find the marginal cost when x equals to 5. First, we will differentiate C of x to get its derivative, which is 4x plus 10. Then, we will substitute it when x equals to 5. So C prime of 5 equals to 4 times 5 plus 10 equals to 30. That actually means the cost of producing the 6th unit is $30. The average cost function. This function helps businesses understand their cost efficiency. The average cost function, denoted as ACX, represents the cost per unit when producing X units of a product. The formula for the average cost function is straightforward, where AC of X equals to C of X over X. Here, C of X is the total cost for producing X units. Dividing by X gives the cost per unit. To analyze how average costs change with production levels, we use derivatives. The derivative of the average cost function, AC prime of X, shows the rate of change of the cost per unit as production increases or decreases. This insight helps businesses decide on optimal production levels. Let's illustrate with an example. Suppose the cost function is 2x squared plus 10x plus 100. Find AC prime of x and compute it at x equals to 5. To find the average cost function, take the cost function and divide it by x, which is 2x squared plus 10x plus 100 divided by x, which equals to 2x plus 10 plus 100 over x. To find AC prime of x, we take its derivative, which equals to 2 plus 100 over x squared. Next, we will substitute it by x equals to 5. 2 minus 100 over 5 squared equals to minus 2. Notice that its rate of change is negative, which implies that the average cost function decreases by $2 per unit when producing 5 units. The revenue function, denoted as R of X, represents the total revenue a company earns from selling X units of a product. The formula for the revenue function is R of X equals to P of X times X. Here, P of X is the price per unit. Multiplying P of X by the number of units X gives the total revenue. To understand how revenue changes with sales, we use the derivative of the revenue function, R prime of X, also known as the marginal revenue. It measures the additional revenue earned from selling one more unit. This insight is crucial for businesses to decide how many units to produce and sell for maximum profitability. Let's look at an example to see this in action. Suppose the revenue function R of x of a company is 50x minus 0.5x squared. Find the marginal revenue when x equals to 10. As usual, we differentiate R of x to get its derivative or its marginal revenue, where R prime of x equals to 50 minus x. Substituting it by x equals to 10, where R prime 10 equals to 50 minus 10 equals to 40, tells us that selling the 11th unit generates an additional $40 in revenue. Next, we'll talk about the average revenue functions. This function is useful for understanding the revenue generated per unit of products sold. The average revenue function, denoted as AR of x, is defined as R of x over x. Here, R of x is the revenue function that we talked about before. Dividing it by x gives the revenue per unit. The derivative of the average revenue function, AR prime of x, helps us understand how the revenue per unit changes as the number of units sold increases or decreases, or we can say it as the rate of change of average revenue. Here's the example. Suppose the revenue function is 50x minus 0.5x squared. We can find the average revenue function by dividing it by x to get 50 minus 0.5x. Then we can find the AR prime of x by differentiating AR of x, and we get minus 0.5. Notice that the rate of change is negative. This means that the average revenue decreases by $0.5 for every additional unit sold. Let's shift our focus to the profit function. This function, denoted as P of x, represents the total profit a company earns by selling X units of a product. Profit is essentially the difference between the total revenue and total cost, where P of x equals to R of x minus C of x. Subtracting cost from the revenue gives the overall profit. Now, let's examine how calculus comes into play. The derivative of the profit function, P prime of x, is called the marginal profit. It measures the additional profit earned from selling one more unit. Mathematically, it is P prime of x equals to R prime of x minus C prime of x. This shows that the marginal profit is the difference between the marginal revenue and marginal cost. Businesses use this to decide optimal production levels and maximize profits. Here's an example to bring these concepts to life. Suppose the revenue and cost function are R of x equals to 50x minus 0.5x squared and C of x equals to 10x plus 100. Find the marginal profit when x equals to 10. First, we'll find the profit function with R of x minus C of x, and we will get 40x plus 0.5x squared minus 100. To find the marginal profit, we differentiate it and get 40 minus x. Finally, we substitute x equals to 10, so P prime of 10 equals to 40 minus 10 equals to 30. So that simply means selling the 11th unit increases profit by $30. And for the last part of application of derivatives in economics, we have the average profit functions, denoted as AP of x, which measures the profit earned per unit sold. The formula for the average profit is AP of x equals to P of x over x. Here, P of x is the total profit. Dividing P of x by x gives the profit per unit at a given production level. To gain deeper insights, we examine how average profit changes with production. This is achieved by using the derivative of AP prime of x, which shows the rate of change in profit per unit as production increases or decreases. Let's break it down with an example. Suppose the profit function is 40x minus 0.5x squared minus 100. Find AP prime of x at x equals to 10. We use the AP of x equals to P of x over x formula to find the average profit function, which is 40 minus 0.5x minus 100 over x. Then, continue by differentiating it to get AP prime of x equals to minus 0.5 plus 100 over x squared. Then we substitute x equals to 10, so AP prime of 10 equals to minus 0.5 plus 100 over 10 squared equals to 0.5. As the rate of change is positive, this means that the average profit increases by $0.5 per unit when producing 10 units. Finally, we are at the second part of this presentation, the washer method, a technique in calculus used to calculate the volume of a solid of revolution. This method is particularly useful when the solid has a hole in the middle, resembling a washer shape. The washer method calculates the volume by subtracting the volume of the inner hole from the outer solid. Imagine stacking tin washers along an axis of rotation to form a 3D shape. The formula for washer method depends on whether the rotation is about x-axis or y-axis, although they are actually pretty similar. The general formula for the volume of a solid using the washer method is V equals to pi times the definite integral of outer radius square minus inner radius square from A to B. This formula works for rotation about the x-axis. For rotation about the y-axis, the outer and inner radius are functions of y, where the outer radius is distance from the axis of rotation to the outer curve, and the inner radius is the distance from the axis of rotation to the inner curve. And AB or CD is the interval of integration. Let's apply the washer method to an example. Suppose you want to find the volume of the solid obtained by rotating the region bounded by y equals to x squared and y equals to 4 about the x-axis. The first step, we define the region and the method. Since the rotation is about x-axis, the inner and the outer radius are functions of x. When we draw the curve and the line of the both function, we can notice that the function y equals to 4 is farther from the axis of rotation. Therefore, the outer radius equals to 4, while the function y equals to x squared is closer to the axis of rotation. X squared is the inner radius. Then, we determine the interval of integration, which are x equals to minus 2 to x equals to 2, because as we can see in the sketch, y equals to 4 intersects y equals to x squared at these points. Step 2, we set up the integral by the washer method formula, where v equals to pi times definite integral of outer radius squared minus inner radius squared from minus 2 to 2, which we then plug in the inner and the outer radius to get pi times definite integral of 4 squared minus x squared squared from minus 2 to 2. Step 3, we evaluate the integral. Notice that we can change x squared squared to x to the power 4. Next, we write separate integrals for each segment, ensuring that the outer and inner radius are correctly defined for their respective intervals. For the definite interval of 16 from minus 2 to 2, the result is 16 times 2 minus negative 2 equals to 16 times 4, then we'll get 64. And for the definite integral of x power 4 from minus 2 to 2, since x to power 4 is an even function, we can integrate them over the interval 0 to 2, which will get 32 over 5, and then we will double the result, so the definite integral of x to power 4 from minus 2 to 2 equals to 2 times 32 over 5, then we'll get 64 over 5. Since we already know the result of both integration, we now substitute them back to find the total volume, where the integration of the outer radius is 64 and the inner radius is 64 over 5. The total volume equals to pi times 64 minus 64 over 5 equals to pi times 320 minus 64 over 5 equals to 256 over 5 pi. So the total volume is 256 pi over 5. The last part of this presentation, the moments and center of mass. Let's start with the concept of a moment. A moment measures the tendency of a force or weight to cause rotation about a point or axis. In the context of mass distribution, Moments provide insights into how weight is spread relative to a specific reference point. Moments are widely used in physics and engineering to understand balance, stability, and rotational effects. Total moment, m, is equals to the sum of mi di from I equals to 1 to n, which is the total number of masses. Mi is the mass of the ith object in the system, and di is the distance of the ith object from the reference point. Center of mass. The center of mass is the point where the entire mass of an object or a system seems to be concentrated. When forces act on the system, it behaves as though all the mass is concentrated at this single point. To calculate the center of a mass in a two-dimensional system, we use these formulas. X for the center of mass equals to the sum of mi(xi) divided by sum of mi, and y for the center of mass equals to the sum of mi(yi) divided by sum of mi. These represent the weighted averages of the coordinates, where the weights are the masses of the individual points in a system. Now, let's look at an example to apply these formulas. Three objects with masses m1 equals to 4, m2 equals to 7, and m3 equals to 9 are positioned at the coordinates 2, 3, 6, 8, and 10, 4, respectively on a two-dimension plane. Determine the moments about the axis and the coordinates of the system center of mass. Our goal is to determine the moments about the axis and the coordinates of the center of mass of the system. The formulas for the moments are mx, or the moment about the x-axis, equals to sum of mi(xi), and my, the moments about the y-axis, equals to the sum of mi(yi). And the center of mass is given by x for the center of mass equals to mx over m, and y for the center of mass equals to my over m, where m equals to sum of mi, or the total mass. We have three objects with the following masses: m1 equals to 4, m2 equals to 7, and m3 equals to 9. Their position on a two-dimension plane are given as x1, y1 equals to 2, 3, x2, y2 equals to 6, 8, and x3, y3 equals to 10, 4. Here's how we solve the example step by step. First, we'll count the total mass, which is m1 plus m2 plus m3 equals to 20. Next, we'll calculate the moments about the x-axis, which is 140, and the y-axis, which is 104. Now, we'll compute the center of mass by the previous formula, where x for the center of mass equals to mx over m, which equals to 7, and y for the center of mass equals to 5.2. And the moments for about the x-axis is 140, and the moments for the y-axis equals to 104. And the center of mass for the system is located at the point 7, 5.2. For visualization, in this diagram, we see 3 points representing the objects in the system. Each point corresponds to a specific mass and is plotted at its respective coordinates 2, 3, 6, 8, and 10, 4. These points are weighted based on their masses, where m1 equals to 4, m2 equals to 7, and m3 equals to 9. In the center of these points, there is a red X mark. This red X represents the center of mass, the point where the entire system would balance if placed on a pivot. Notice how the position of the center of mass at 7, 5.2 is influenced by both the positions and the weights of the masses. Heavier masses, like m3 equals to 9, at 10, 4, pull the center of mass closer to their location. Conversely, lighter masses, like m1 equals to 4, at 2, 3, have less influence. This visual helps us understand that the center of mass is not necessarily at the geometric center, but it is instead determined by the distribution of mass across the system. In conclusion, we've seen how mathematics plays a vital role across various fields, from derivatives in economics to optimize profit, to the washer method for calculating volumes, and the center of mass and moments for balancing systems. These concepts show how math helps us solve real-world problems efficiently and effectively. Thank you all for your attention. I hope this presentation has shown the power and practicality of these mathematical tools. Thank you.